so that they're not allowed to swear. Okay, hello students, how very nice to see you. It's teacher Mark again. Today I should have been doing juju in the laboratory, but when I got to the laboratory and I sorted out the chemicals, they told me there is no Wi-Fi because they are upgrading the whole school system, which is a bit annoying. But anyway, and here's the Church Army High School just coming in. So we'll just wait for them to connect. And with Church Army, we get a newsreader. If some of you will remember, we have somebody who is very, very good at pronouncing things. Okay, I'm going to assume they're there. So here we go. Right. I'm going to start with the end of last lesson, and I'm going to go into hard water, soft water, amphoteric behavior, and so on, all of which would be better if I was showing you the chemistry, but I can't today. So, are you ready? Are we ready? Oh, we're ready. Thank you, Kabiro. Well done. Kabiro, I'm ready. Ushirika, are you ready? Yeah, we're ready. Okay, here we go. So last time, I'm going to share my screen. Last time we were talking about Trona, and I showed you a really silly picture, which was this one, which was about the deadliest lake, Natron, which is a very alkaline lake. This is not a true picture. This is a made up silly picture. I just thought some of you might go, that's pretty silly, and it is. Lake Natron is very unusual in that it is very, very alkaline, and it is alkaline because it is surrounded by land and the water evaporates, and all the water that comes into the lake dissolves the salts in the mountains around, and then the water evaporates, so it becomes more and more concentrated. And it will, if anything dies in the lake, it will cover it with salt, with Trona. And that is what it looked like. And what we said was, we have our own two very big processes in Kenya at Lake Magadi, the soda company, and Lake Magadi, very beautiful, lots of flamingos, but also very beautiful pictures, but also a big factory. And the big factory looks like this, which is not attractive, but it is for getting sodium carbonate out of the lake, because sodium carbonate is very valuable. We also have further up the coast. Oh yeah, sorry, one thing I should have said was this here. Trona is a double salt. A double salt is when two salts, which are slightly different, are joined together. And if we add that together, we get this: 3 sodiums, 1 hydrogen, 2 carbonates, and 2 waters. And when this is heated up, it becomes sodium carbonate, which is what we want. So what I've done is then I said, okay, it's a very useful chemical. But also further up the coast, just past Malindi on the way to Lamu, is a place where a lot of salt is harvested, and salt is very, very similar solubility at all temperatures. Very similar solubility at all temperatures. That's it, the black triangles there. Some people say it decreases a little bit in solubility with temperature. That doesn't matter. They're not quite right, but it doesn't matter. And this is the point that when you pile it up, when you trap the salt water and you let it evaporate, you get salt like this, and it's piled up and then turned into large towers. For those of you who want to see a summary of this, here it is. Here's the summary of it. So sodium chloride and Trona, that's sodium sesquicarbonate, the mixed salt, here is dissolved in the sea or in lakes, and we use what they call natural fractional crystallization. Fractional crystallization, some things dissolve at different temperatures, different salts dissolve at different temperatures, and some of them will be precipitated as it cools down. This your teachers will get anyway if you want it. The point is that when we take trona, trona is less soluble in hot temperatures, and so we get the trona out in the daytime. Sodium is less soluble when it goes colder, slightly, and so it's got out at night. So the trona comes out in the daytime when it's hot, and sodium chloride when it's at night. Both of them is just picked up, dug up, crushed. The sodium is just bagged as it is, but the trona is heated up and produces soda ash, which is washing soda, which is sodium carbonate. Okay, so the one is sodium chloride, the other one is sodium carbonate. That is just a simplification of the whole process. So today what we're going to do is we're going to look at the other bits, not quite all of it, because some of it is better practical. We are going to look at some of these parts. This is the syllabus. What we're going to look at here first is water hardness. You probably know a little bit about water hardness. Then we're going to look a little bit at amphoteric oxides and hydroxides and precipitation reactions. And then we're going to look at complex ions. We're going to leave this bit, this second bit down, until I can show you it in a laboratory. Okay, so first, hard water. Second, amphoteric chemicals. That's what we're going to do today, and I hope it's hope it's useful. So here we go. Welcome to Dandora's chess opposition. St. Teresa's, very nice to see some of you there. It's really good to see two schools there. Excellent. So here we go. So this is all going to be about hard water. I'm going to explain it with a diagram behind me. But first we're going to go through something, going to show you a very simple video which should explain this a little bit better than I will. So here we are. So hard water. Everything that we are doing is to do with the solubility table we came across last time. And what is important to remember is that sodium and potassium salts are all soluble, but most carbonates and hydroxides are insoluble. Okay, so calcium carbonate, zinc hydroxide, iron hydroxide, all insoluble, but sodium and potassium soluble. That is how we will explain a lot of things. So this is firstly about hard and soft water. This is not worth copying out, but I'm going to just tell you that hard water contains calcium and magnesium ions. That is worth writing down if you're going to make any notes. Calcium and magnesium ions. It has a higher than 7 pH. That means it's slightly alkaline. It is generally, if you buy bottled water, which is a silly way of buying water, but if you buy bottled mineral water, it is always hard water. And most well water is also hard. Soft water is what comes out of the sky. So here at the moment it is raining, and that rain is soft water. It is also produced by distilling. So if we heat up water and we evaporate it and condense it, it will be soft. And it is also the water that is produced from the sea by reverse osmosis. There are several plants for reverse osmosis in Kenya. Here's a little, not really an experiment, but it just shows you what the difference between them is, I hope. So we'll go without, we'll go without his sound. Okay, here we have 2 buckets of water, 2 pieces of soap. Soap does not dissolve in water very easily. They are just pieces of soap. In the hard water, if we start to mess about with the soap and we try to wash our hands, very quickly we see it forms white precipitate. The precipitate is what we call scum. Okay, so I'm just going to pause that there. Here we are. In hard water, soap makes scum. That's very important of its own. That's an important idea on its own, because that means that washing your clothes with hard water and soap will not get your clothes clean. It will leave scum on them. Okay? In soft water, something very different happens. If we try to wash ourselves with soap in soft water, we get bubbles, what we call a lather, very, very quickly. So there must be something in the water that makes the hard water very different from the soft water. Okay, so that's an important idea, that hard water makes scum and soft water makes bubbles. Now that scum doesn't go, and nor do the bubbles. Hard water can be turned into soft water in a way that we will discover in just a minute. You may have seen this before. It's very important that you have the idea that this is what's happening. Okay. So first thing to know, hard water is not very good with soap. So with soap, only soap, not detergent. So if you have something like shower gel or detergent like for washing clothes, then that chemical makes the hard water soft. But ordinary soap, the soap which we get in a bar, that soap will make a scum with hard water. But with soft water, it won't. That's really important. That's something you need to know, because it's something that they ask questions about. They say, why should you not wash your clothes in hard water with soap? Okay, back to the board. So the question is, how does hard water form and why? And I'm going to stop sharing that, and I'm going to show you a little silly picture which I'm going to draw behind me on the other board. Okay. So, over here, hello. Let us imagine we have a hill like this, and coming away from the hill is a river. Okay. Now, a lot of water comes from clouds into hills and through and coming out in rivers. The rivers go into the lakes or into seas and so on. I hope you can see that. Let me see if I can see whether you can see the picture. Picture's got a little bit too much shine on it. Let's just see if we can make it a bit. All right, still too much shine. I'll move it across a bit. I'll just move the whole picture across a bit. Okay, so we have a hill, it's going to rain, here's some clouds, and out of the bottom of the mountain comes a river. Okay, now mountains can be made of many different kinds of rocks. So we can have silicon dioxide, very common. It breaks down to make sand. Let me just make sure you can see that. That's okay. Silicon dioxide. We have calcium carbonate. We have magnesium carbonate. We have calcium chloride, calcium sulfate, many different rocks, aluminium oxide, and so on. Okay, these are all types of minerals which are in mountains. Okay, minerals which are in mountains. When the water falls on a lot of these chemicals, nothing happens. So things like silicon dioxide do not react with water at all. The water will just run off. In northern Nigeria, where I was a child, there are some silicon dioxide, very big mountains, and the water is not absorbed by them at all. The same is true of aluminium oxide. Aluminium oxide doesn't absorb water at all, but some of these chemicals do. And calcium carbonate and magnesium carbonate and calcium chloride and calcium sulfate, they all partially dissolve in water. What happens is this. Water and carbon dioxide makes carbonic acid. Carbonic acid is a very, very weak acid. A very weak acid. It's so weak that if you test its pH, it's only just over 7. But over millions of years, that acid dissolves calcium carbonate and magnesium carbonate. And what happens is that we get out calcium hydrogen carbonate and magnesium hydrogen carbonate. And both of these are washed through and into the river. The calcium chloride and calcium sulfate also dissolve and go into the river. So calcium chloride, partially soluble, calcium sulfate also partially soluble, dissolve in the river. If the river ends up in our home, if that's the source of our water, then it will contain not just H2O from the cloud, but calcium hydrogen carbonate, calcium bicarbonate, magnesium hydrogen carbonate, calcium chloride, calcium sulfate. Now, hard water is often described as having two different types. So hard water can be called temporary and permanent. This is a bad word for it, permanent, because it is not permanent. But this is when they didn't know much about it. And temporary means it can be removed, turned into soft water simply by boiling. Okay, so boiling makes it soft. Permanent, boiling has no effect at all. Okay, no effect. So if I have 2 samples of water and I boil the water and it becomes soft so I can get bubbles with the soap, then it was temporary hard water. If I boil it and it is still hard, in other words, it still forms the scum, then it was permanent. That's an important distinction, and it's something you need to know. So, which of these chemicals make temporary and which ones make permanent? Let's make it into a little table. So I have temporary and permanent, or what they call that. And the solution of which chemicals? Temporary is calcium hydrogen carbonate and magnesium hydrogen carbonate, and permanent is calcium chloride and calcium sulfate, or magnesium chloride and magnesium sulfate. The effect of boiling. So what happens when I boil it? Temporary, it goes into soft water. Here, permanent, there is no effect at all. So temporary hard water, boiling makes it soft. Permanent hard water, boiling has no effect on it. Okay? But I said it isn't really permanent. So if it's not really permanent, if boiling has no effect, how do I turn it soft? Well, that's what we're going to talk about next. Hello again. So what I want you to know is this. In a glass of water, there may be many chemicals dissolved. There may be all sorts of ions. And it's the Ca2 plus or the Mg2 plus that makes it hard water. But if the Ca2 plus and Mg2 plus in here is attached to hydrogen carbonate, then just by boiling it, I turn it soft. On the other hand, if it is attached to sulfate or chloride, then boiling it has no effect on it. And what I'm going to do in a minute is I'm going to show you why I'm going to write equations so you can see it. But I said hard water is never properly permanent. Permanent just means that if you boil it, it goes soft. So I take the water, I boil it, I put the soap in it, it makes bubbles. It was temporary hard water. Okay, here we go. Sorry. Okay. So I'm going to extend the table now. So if boiling turns temporary into soft, permanent no effect, what other things can we do? Well, we can also add Na2CO3. Na2CO3 is washing soda. It's the chemical which is one of the chemicals which is in washing powder. And it has exactly the same effect as boiling on temporary. But here it doesn't do the same sort of thing. And the last thing that we have to know about is called, ion exchange. And I'll explain what ion exchange does. But this is turned soft, and this is also turned soft by ion exchange. And I'm going to show you how it works. So ion exchange is, like its name suggests, it removes one ion and replaces it with another one. And how it works is this. We have a long tube, and in the long tube we might have a tap on it. I'm going to have a cup down here, and I'm going to pour in hard water. So hard water contains Ca2 plus Aq or Mg2 plus Aq. In here we have a lot of beads, and the beads are often resin. Resin is the sticky stuff from some trees. So there will be many pieces in here like this. If I look at one of these pieces here, it's like this, and on the outside of it are Na plus sodium ions. And the Na plus ions are stuck to it like this. As the calcium goes through and between these ions, they swap. So the water comes through, and in here, the Ca2 plus comes in, and as it goes past this, Na plus goes out and the Ca sticks to the resin. So all the calcium comes in and sodium ions come out of the bottom. So into the top I have Ca2 plus, whoops, Aq, and out of the bottom I get Na plus Aq. All right, so the water goes straight through, the calcium ions stick to all of the particles in here and swap for the sodium. Excuse me. So Ca2 plus in, sodium out. Some people have a water softener in their house. So they have a big tub with this chemical in, which is to take all of the calcium ions out. It's not actually very good for us. Na plus ions are not very good for us. They can give us high blood pressure. They can affect babies. Very, very small children should not have too much sodium ions, too many sodium ions. So it's not very good for them. So softened water using ion exchange is not a very good idea. Okay. All right. So boiling, adding sodium carbonate removes temporary hard water, the temporary hardness, and doing ion exchange removes all hardness. Distillation also removes all hardness, because when we distill water, the water evaporates, recondenses, and the salts are left in the flask. So that also does it, but it's very expensive. Boiling is very expensive. You need a lot of fuel, so it's not very good. Okay, what are the advantages and disadvantages of hard water? Okay, hard water tastes better. It's much, much nicer to drink. It is better for making beer, a lot better for making beer. And it is good for your teeth and your bones. It makes them stronger, so hard water is good for that. Soft water is much better for washing clothes. I will just write these on the board now behind me so that you have them. Okay. So this is ion exchange. Okay, advantages, disadvantages, hard water, soft water. Hard water, teeth, bones, it's good for them. Taste, it's much nicer to taste. And it's very important for making beer. You might not think that's important, but a lot of money is made by making beer in Kenya, in most countries. Soft water, soft water is good for washing. So it is great if you own a laundrette, if you do a lot of clothes, if you wash a lot of clothes for other people, you would want soft water, not hard water. So it's very, very good for washing. Much, much better than hard water. There are also some other things which are not so important. There are some chemical processes. Disadvantage of hard water is scum with soap. Like we saw when it was in the bucket, it makes that white stuff. So scum, sorry, that doesn't look like scum, SCUM, that's just white stuff, a precipitation. Scum with soap, and we also get what we call a lime scale whenever it is heated. So in kettle, in a boiler, anywhere where it is heated up, you can get lime scale, which is hard white stuff, which can block up pipes and so on. Soft water disadvantage is mainly to do with these things. So it's not good for teeth, bones, beer. It's not good for them. It's very poor for making beer. It doesn't give you any calcium or magnesium for your bones, your teeth, and some of the other things that work inside you. Okay, so that's the advantages, disadvantages, hard water, soft water. So this is the nicer one in all sorts of ways, but it causes problems when we heat it up. Okay, I hope you could see that okay. All right, here we go. So I'm going to move on, and now we're going to move on to what is called amphoteric. Oh, here's an exam question. Here's a little simple exam question, which shows you the sort of exam question they can ask on hard and soft water. Have a look at it for a minute. So here we have sample 1, 2, and 3. And this is the amount of soap which is needed to make a lather, to make bubbles, okay? So the hard water will produce bubbles, a lather, eventually, when all the hardness has been removed. And they do it when it is boiled, when it isn't boiled, before it is boiled, and then after it is boiled. And sample 1 does not change. Sample 2 does not change. Sample 3 changes. Now, which sample is likely to be soft? And explain. Would anybody like to tell me why they think sample 1, 2, or 3 is the soft water? Anybody like to tell me? Perhaps switch on your microphone and have a go. 1, 2, or 3. Which one is, whoops, sorry. Which one is soft? Tell me why. Would our newsreader from Church Army High School like to tell us? And if you know the answer to that, which one of sample 1, 2, and 3 is temporary hard water? Which one is temporary and which one is permanent? So which one is soft, which one is temporary hard, and which one is permanent hard? Anybody willing to put on to have a go? Either to write it down or to turn on the microphone and tell me. Have courage.
It's sample 3.
Sample 3. Dandora Girl says sample 3 is temporary. What the first question is, which is soft?
Which is soft.
Church Army, which is soft? Dandora Girls, which is soft?
It's sample 3.
It's not sample 3. Dandora, show me that again, please.
Not sample 3.
No. Which one is soft? Wait a minute. Let's go back. Look. at this.
It is sample 2.
Oh, well done. Well, it has to be sample 2 because we've had sample 1 and I've said no, and sample 3 and I said no. Look, in this demonstration, let's go up to here. No, here. And I'm going to stop it. Hang on. There. So, which one is soft is the one which makes the bubbles most easily. Okay? So with hard water, it will eventually make bubbles, but the soap has to react with all of the hardness first. So this one here was soft on the left, and on the right is hard. But eventually, if he kept going, he would get bubbles off the hard water. It would just have to remove all of the hardness first. So let's go back. Oh, sorry, you may not. Sorry, I don't think you saw that on my screen sharing. I meant in the 2 buckets, the first one to give all the bubbles was the soft. Okay, so here's the question again. Ah, come on. Sorry. Okay. So here's the question. So which one is soft is sample 2. Sample 2 is the softest because it makes the lava most easily. Okay, the one which makes bubbles most easily is the softest water. The other 2 are both hard. But the one here, sample 1, is the hardest because it needs the most soap to be added. But it also doesn't change it when it's boiled. If it doesn't change when it is boiled, it is what we call permanent hard water. If it changes when it is boiled, then it is temporary hard water. So in this question here, sample 1 is permanent hard water. Sample 2 is soft water. Sample 3 is temporary hard water. So it was hard, but after boiling, it takes the same amount of soap as sample 2. That means all of the hardness has gone. Okay? Okay, let's move on. So this is about amphoteric oxides and hydroxides. Amphoteric is a funny word. Some people think it should be pronounced amphoteric, but it's not. It's amphoteric. Amphoteric chemicals work in a particular way. So we're going to have a look at somebody doing a simple, let me just get to there. A simple experiment. Whoops. Simple experiment just to show the difference between amphoteric and not. We'll just pause it for a minute. Okay, these are chemical demonstrations from Ohio University. We use them quite a bit, and Cambridge University also. So let's just stop it. Okay, come on. So here we have some samples of chemicals. Go away. Come on. Samples of chemicals, and I have iron 3 on the left-hand side and aluminium 3 on the right. This is the iron 3 ions, Fe3 plus Aq, is having sodium hydroxide added to it, and on the right the same to the aluminium. I'm going to write equations in just a minute, but I want you to understand what's happening here. So the iron has precipitated and the aluminium has also precipitated. They are now going to pour a similar amount of it into 3 beakers. This one is going to be a control one. Hang on. I'm sorry, are you not seeing the film? hang on, let me just see. Were you seeing a film then or not? Were you seeing a film or not a film? Okay, my apologies. Hang on, let's go back. Let's see if we can get it. Okay. Now I think you can. Okay, here we have some iron 3 hydroxide, FeOH3, and it's being poured into 3 different beakers. One is going to be a control so we can see what happens. And on the right, we have aluminium hydroxide. To the first one, we are going to add nitric acid. Now, it's not very easy to see what happens here, but when she stirs it, the precipitate disappears and it goes transparent. It's not easy to see that, but I will tell you what's happening in a minute. Now she's going to add sodium hydroxide to it, and you will see it even gets thicker. It does not get any thinner at all. Okay, so this dissolves in acid but not in alkali. Now let's add the acid to the aluminium hydroxide, and it dissolves or goes a lot lighter. And if we add sodium hydroxide to this, add the sodium hydroxide and stir it, it disappears. Okay, now this is quite important. So the idea is that the iron 3 hydroxide here, just out of the way, the iron 3 hydroxide here, if you add acid, I think maybe you can see it is more transparent here. But if you add alkali, acid dissolves it, alkali does not. In aluminium's case, if we have aluminium hydroxide to start with and we add acid, it mostly dissolves. If we add sodium hydroxide, it does dissolve. This is what we mean by amphoteric. So iron 3 hydroxide is a base and reacts with an acid, but not with an alkali. With aluminium hydroxide, it acts as a base with acid, but it also acts with alkali. That makes it amphoteric. So I'm going to write that on the board. That's an important idea there. So I hope you can see that. I'm now going to write it on the board. So if we have a metal oxide or hydroxide, it could be a base or basic, or it could be amphoteric. amphoteric. The basic ones react with acid to give us salt. Acid plus base gives salt and water. We did that last time. The amphoteric ones, they react with the acid to give us salt, and they react with alkali to give what we call a complex. We'll see what that is in a minute. So in the example that they did on the picture there, we had iron hydroxide. This is a base, and iron hydroxide reacts with an acid. So it could be hydrochloric or sulfuric or nitric. I'll use hydrochloric, they use nitric. And it will make a salt. So Fe will make iron chloride and water. To balance this, I need 3 of these, and it will make 3 waters. That is a very simple reaction. You might think, oh, that's a really difficult equation. Don't worry about that. Think if the metal oxide is basic, it reacts with an acid. But the amphoteric one reacts like this in exactly the same way. Like this could be aluminium here. So I could change this to aluminium and it would be exactly the same. AlOH3 plus 3HCl goes to AlCl3 and water. Okay, that's not a surprise. But it also reacts with alkali. And when it reacts with alkali, it forms something different. And what I'm going to do now is to show you what that is. But firstly, I just want you to get this down in your head. Metal oxides or hydroxides can be basic or amphoteric. If they are basic, they will react with an acid to give us salt and water. Here is an example. These do not react with alkali at all. So if I add alkali, nothing happens. It gets more sludge. If it is amphoteric, it will follow this pattern if it's reacted with an acid, but if we react with an alkali, something else happens. And it forms a complex, and I'm going to show you what that's like now. I'm going to take zinc hydroxide. So zinc hydroxide is ZnOH2. And I'm going to react the zinc hydroxide, with sodium hydroxide. And it always involves water as well. Okay? And what happens is that the zinc hydroxide reacts with these and dissolves, like the aluminium then did, because zinc is also amphoteric. Excuse me. And if we have two of these, it forms a complex over here, which is ZnOH4. Now that's a bit weird. ZnOH4 is a little bit of an odd thing to have. This is here because normally we would have the sodium in here, and we're not going to bother with the sodium. We're just going to form this ZnOH4. And what we do is we show it like this in square brackets. And then the whole charge is on the outside of it. So I'm saying that this is necessary, but in this equation here, we could write it like this. Sometimes, and your teachers may well show it with sodium hydroxide, in which case you'll need the water. So I'll just move this here, this. And the charge on the whole thing, this is what we call a complex ion. The charge on the whole thing is the total of the zinc and the hydroxides. Now the zinc is Zn2 plus, each hydroxide is 1 minus. So overall, this will be 2 minus, because this is 2 plus, and each one of these is minus. So we've got 2 plus, 4 minuses, 2 minus overall. If I did it with aluminium, I would have AlOH3, because aluminium has a valency of 3. I would need 3 OH minuses to form AlOH6, and the total charge 3 plus, 6 minus, 3 minus. Or sometimes they write it with just 1 OH minus, and it becomes AlOH4. Now, if I were you, I would remember this one. Now this will be 3 plus, 4 minus, 1 minus, because there's 4 in this one and 4 in this one, so it's easier to remember 4. So if I were you, I would remember this. In KCSE examinations, this is perfectly fine. So remember this. Okay. So I'm going to come back to my other screen. I'm sorry there's a bit of light on that. I'll write it. I'll write it a little bit higher later. So, amphoteric. Basic react with acids. Amphoteric react with acids and alkalis. They both dissolve to form a salt or a complex if it's the alkali. Now you go, oh, this sounds really hard. This sounds really hard. This is something that I cannot get. The point about this is not to be able to write equations, but it is because it is in paper 3. And in paper 3, you sometimes have to do some identification. And if you add sodium hydroxide to a precipitate and it dissolves, you can go, it's amphoteric. I don't remember how to write the equation, but I know it's amphoteric. If you add acid and it dissolves, it could be amphoteric, but you would need to add sodium hydroxide. And if it dissolved, then it would be. Okay. So I'm going to write one pair of equations that I think you might find useful for zinc hydroxide, and we're going to just put them down now so you can write them down and look at them and try to understand what's happening. And then we're going to leave amphoteric and move on to more of complexes. Okay, I know it's a bit hard. Hey, I know it's a bit hard. Don't go to sleep. Think about the chess. Think about chemistry. See, chemistry and chess both start with CHE. Whoa, they must be the same thing. Just as good. Whoa, that's amazing. That's okay. For those people in Mathare Mixed and Church Army High School and so on, I'm sorry, we're just having a joke with Dandora and St. Teresa's because they were playing a game of chemistry earlier. Sorry, chess. Right, so I'm going to write the equation and see if you can work out what's going to happen before I write it. See if you can work out. Here we go. Okay, I'm going to take some zinc hydroxide. It is amphoteric. I'm going to add some nitric acid. What forms? I'm going to take some zinc hydroxide and I'm going to add some sodium hydroxide. I'm not putting the sodium here, it doesn't matter. What forms? See if you can work it out. Zinc hydroxide, this is acting as a base here, and it's actually acting as an acid here, because that's a base plus acid, and this is a base, and therefore this is reacting as an acid. So see if you can work out what forms here. It will be two things here and only one here. See if you can work it out. Has anybody managed to write write the equation for either one of those? Zinc hydroxide and nitric acid. Nearly, very, very nearly. Okay, very, very nearly. There's just something not quite right with your first one. That's very good, but zinc nitrate. Well, zinc has a valency of 2 and nitrate has a valency of 1. So zinc nitrate would be zinc with 2 nitrates. Come, Mathari Mixed, I know you can do this. Look at you, you're looking come on, yes! Good, let me just have a look. Oh, yes, I'm loving that. That's really good. That's very good indeed. Ah, that's more like it. That's more like it. Very good. Well done, Dandora. Well done, Mathari Mix. Great. Church Army. Why didn't you tell me? Why didn't you show me? So what about the one with the alkali then? Dandora, Mathari? Anybody? Nearly, but zinc nitrate is going to be Zn and 2 NO3s, and your second one is not balanced. If you have a look at it again, it's nearly right. I mean, you've got the right idea, certainly, but we need to get a little bit more precise with these things. Second one, Mathari. Second one, Dandora. Hang on, let me just pin you. That's much better, much better. The second one is completely right, but the first one, your nitric acid is not balanced. Have a look at your nitric acid. Church Army. Oh, sorry, Mathari. Hang on just a minute. Let me just make you large. Yeah, only that's very good. Your product is exactly right, but your hydroxides are not balanced yet. Mathari, have a look at the hydroxides. Dandora, come on, Dandora. You might be good at chess, but you haven't done the second one yet. That is correct. Oh, hang on. Yes, that is correct. Very good. Very, very good. Well done. Well done. As usual. Come, Mathari Mix. Come on. Oh, yes. Oh, yes. Lovely. Well done. Beautiful. Okay. So I'm going to do it now on my board. Make sure we can do it. Okay. So this ZnOH2 will form ZnNO3 2 and H2O. 2 nitric acids here, 2 hydrogens, 2 hydroxides, 2 waters. And this one here will just need 2 of these to turn it into ZnOH4. Now in square brackets, it's important they're not curved brackets, square brackets. Total charge, well, that's 2 plus. Each one of these is minus. Zn2 plus, 4 minus, 2 minus. If we look at this top one, we can turn it into an ionic equation, because these will be split up. This will be ZnOH 2, this will be 2H plus and 2NO3 minus goes to, this dissolves, so Zn2 plus and 2 nitrates, and this doesn't split up, 2H2O. I know that's a bit long. So ZnOH2, that's a solid, so it doesn't split up. This is AQ, so it does. This is AQ, so it does. That's L, so it doesn't. So let's look at what we can remove to turn it into an ionic equation. The nitrate here and the nitrate here can go, and therefore ZnOH2 plus 2H plus make zinc ions and waters. Zinc hydroxide, H2H pluses, zinc ions, which are in solution, and water. Okay, so, and this is the important bit. So if I take copper hydroxide, and copper hydroxide is not amphoteric. So here's copper. I'm going to do copper hydroxide and hydrochloric acid, and it will form copper chloride and water. 2 of these, 2 of those. And if it was amphoteric, it's not, then it would react with hydroxides, 2 of these, to make CuOH4, 2 minus, because 2 plus and 4 minus. And I saw an exam in which they said, which one of these is wrong and why? And the answer is this one is wrong. And that is because this is not amphoteric. Therefore, does not react with alkali. That's really important. Now, the only amphoteric metals you are going to come across are aluminium, lead, and zinc. Those are the only amphoteric ones. If you can remember that, you remember only these guys will do this. Only these guys will form the what's called tetrahydroxy. This one here. Only these will react with alkali. All other metal hydroxides will react with acids, every one of them, but only these 3 will react with hydroxide, will react with alkali. That's really important. The reason that is really important is that if in paper 3 you had an experiment and they said, oh, here's chemical X, and you don't know what it is, and it is in solution, and they say add acid to it, add alkali to it, and make it precipitate first, I'll talk about that, make it into X hydroxide, and then add acid to it and add alkali to it, and if both of them dissolved, it is one of these. And if only the acid dissolved, it's not one of those. That's really important. That's a simple chemistry paper 3 practical thing which has come up many, many times in analysis. Okay. So in other words, these guys will precipitate in sodium hydroxide and then dissolve, and none of the rest will. So we finish with this. We're going to finish with a couple of little equations which I'm going to show you. If I take any metal, iron 3 hydroxide, sorry, iron 3, and I put in some sodium hydroxide, it will give a precipitate. I know it's a precipitate because this is AQ. I will need 3 of these. They are AQ, and that is solid. The same would happen with any metal, apart from sodium and potassium. If I take copper, copper 2 plus, AQ, plus 2OH minus, AQ, makes Cu, OH2, solid. But if I take zinc 2 plus, AQ, and add 2OH minus, AQ, it makes ZnOH2 solid. But when I add some more sodium hydroxide, that disappears. This doesn't, they just get thicker. This one disappears. That's really important. It's one of these 3 amphoteric chemicals. This is called precipitation because it's forming a solid each time. But then this, if I add more ZnOH2 plus 2OH minus, turns into the thing in square brackets, which is AQ again. That's amphoteric. Okay. Hello again. Okay, that's the end for today. I hope I will be in a laboratory next time. I'm sorry this has been quite dry. It is quite hard chemistry, I think, quite hard equations and so on. But it is very important. If you can get the basics of it, it will be okay. So today we have done hard water, soft water. We have done some stuff about precipitation. We have met amphoteric chemicals only, zinc, lead, aluminium, and only they will redissolve in alkali. So it's time to go. It's time to get out in your sunshine. Here we have, we have sunshine. Wow, that makes a change.
Have we?
Yeah.
I've got grey clouds here.
Yeah, sunshine. Wait, hang on.
Well, that's England for you, isn't it?
That's England for you. Wait a minute. I'll show you. Promise. Oh, too much brightness.
It's far too much brightness.
Far too much brightness.
Yes.
Look at that. Sunshine.
Okay,
Oh, my God.
Mathari Mix, we're trying to show you something.
It's beautiful.
Sorry? Okay, let me just have a look. Hang on, I'm coming back to me. Hang on.
Oh, Happy Easter.
Happy Easter.
Happy Easter.
Happy
Yes.
Easter.
Thank you, Mathari.
Happy
Very
Easter.
happy Easter to everybody. I hope everybody has a fantastic Easter, a lovely Easter. Go and look after your families. Let your families look after you, and be great.
Oh, and
Happy
a happy
Easter.
face from
Happy
Gaia.
Easter with a smile.
Is
That
it a
is a-
smile or a frown?
That
It's
is
a
a
smile.
lovely smile. That is such a good smile. Hey, tomorrow is a holiday, isn't it?
Mm-hmm.
Yes.
Ah, no chemistry.
No books.
Ah,
No books.
no chemistry.
Mr. Gatehouse is very sad because there's no physics.
Oh, tough on him, eh?
Yeah.
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 I bet he's weeping into his pint.
Yes.
Anyway.
Yes.
So I hope everybody has a lovely time. Look after yourselves. Be good. Be great. And keep doing chemistry. Oh, yes, Mathari. What do you mean, no?
No chemistry during Easter.
Oh, right. Okay. Okay. I thought you were doing this. Oh, dear. No chemistry. Take chemistry off. Practice your chess, though.
I tell you what, Mark,
Especially St. Teresa. You need to practice your chess.
Mark, have you got just a moment to hang on?
Yes, I have.
Okay. Well, I'm going to. Bye-bye, everybody.
Bye-bye, everybody.
Bye-bye.
Go
Bye-bye.
have some fun. Get outside. Get outside.
Enjoy your Easter.
Enjoy your Easter. Go. Bye.
Bye-bye.
Lovely to meet you, St. Teresa's. Bye. Bye, Mathari.
Teacher
Bye.
Mark, you need
Dandora.
to stop the recording.
Bye, Dandora. Bye, Michael.
Bye. Teacher Mark, stop the recording.
Bye.
I will stop the recording.